Hello, bachcho. Welcome. Today, we are going to tackle a very important topic from our second unit, electrostatic potential and capacitance. The topic is dielectrics and polarization. Now, I know. The name sounds a bit heavy, hai na? But don't you worry at all. By the end of the session, I promise you this entire concept will be crystal clear and you'll remember it for life. And most importantly, we'll learn it in a way that is 100% exam safe, so not a single mark is lost.
Okay, so what's our plan for today? Simple high. First, we'll start with a fun, everyday question. Why do little bits of paper stick to a comb? Then we'll get introduced to the main characters of our story today, the dielectrics. After that, we'll dive into the main process, polarization, and see what happens to atoms when they're under a bit of stress. Then we'll figure out how to measure this effect using something called the dielectric constant, K. And finally, of course, we'll wrap it all up with a quick summary and see where we go from here. Chalo, ready? Let's begin.
All right, let's get right into it. We're going to start by solving a little everyday mystery. Something you've all seen for sure, and you've probably even done it yourself 100 times. But maybe you never really stopped to think about the actual physics going on behind the scenes. So think about this. I'm sure every single one of you has done this little magic trick, right? You take a plastic comb, rub it on your dry hair, and suddenly it can pick up these tiny little bits of paper. But have you ever really wondered how that works? I mean, the comb gets charged. Okay, we get that. But the paper pieces, they're neutral. They don't have any net charge. So how on earth can a charged object attract a neutral one? It's a great question, isn't it? Well, this is the exact puzzle we're going to solve today. Okay, so to figure out this so-called magic, we first need to properly understand the special materials that are involved here. And that brings us to our next section, where we finally meet the dielectrics. They're the ones holding the secret. So look, in the world of electrostatics, materials are basically divided into two big teams, okay? On team one, you have the conductors. Think of copper, iron, any metal. And these guys, the electrons, are completely free. They can just roam around the entire material wherever they want. And that's exactly why they are so good at conducting electricity. But then you have team two, the dielectrics. This is the team that includes plastic, glass, and yes, the paper from our experiment. In these materials, the electrons are bound. They're on a very tight leash, tied to their own atoms. They cannot just get up and move around. And because they can't move freely, dielectrics are what we call electrical insulators. To make this super simple to remember, let's use an analogy. Let's just imagine a dielectric is like a very strict classroom. Got that picture in your head? Now, in this classroom, the students are our electrons, and their desks, well, those are the atoms. And the number one rule in this classroom is very simple. Students are absolutely not allowed to leave their seats, ever. They are bound to their desks. But here's the crucial part. Just because the students are stuck in their seats doesn't mean they're completely frozen, right? Imagine the teacher, who is like our external electric field, stands at the front of the room. Now what can the students do? They can't get up and run around, of course not, but they can all lean to one side. They can shift a little bit in their seats, and this little leaning action, this is the secret superpower of all dielectrics.
So this leaning of the students, what do we call it in the proper language of physics? Well, this brings us to the absolute core concept for today, bacho, polarization. Let's take a look at what is actually happening deep inside that dielectric material.
Let's break this down step by step. It's really simple if you just follow along. First, look at step one. When there is no external field, the atom is perfectly happy and symmetrical. See? The positive nucleus is right in the middle of the negative electron cloud, all balanced. Now, for step two, we switch on an external electric field. We'll call it E0. As soon as we do this, the positive nucleus gets a little push in the direction of the field, while the negative electron cloud gets pulled in the opposite direction. This causes the whole atom to kind of stretch out into an oval shape, which you can see in step three. This stretched out atom is now what we call a tiny electric dipole. Okay, now imagine millions of these atoms all doing this at the same time. Together, as you can see in step four, they create their own small internal electric field, let's call it EP, which points in the opposite direction. And this leads to the final amazing result in step five. The net field inside the dielectric, which we'll call E, is now weaker than the field we started with. Why? Because E is simply the original E0 minus this new internal field EP. So this entire process that we just saw, the stretching of the atoms, the creation of tiny dipoles, it has an official name, and the proper exam-safe name is polarization. Formally, we say that polarization is the process where an external electric field induces a net dipole moment in a dielectric material. In simple words,
It's just all that stretching and aligning of atoms that we just talked about. Simple, right?
And with this knowledge, we can finally solve our comb and paper mystery. So what's happening? The charged comb creates an electric field. This field then polarizes the atoms inside the neutral pieces of paper. So on the side of the paper that's closer to the comb, a tiny opposite charge gets induced on the surface. And since that opposite charge is closer, the force of attraction is just a little bit stronger than the force of repulsion from the charges on the other side. And that's it. That's why the paper jumps up and sticks to the comb. Mystery solved. Excellent work. So now we know what polarization is. But are all materials equally good at it? Of course not. So how do we measure this ability? How do we put a number on it? Well, that brings us to our next topic, the dielectric constant, which we write as a capital K. You can think of K as a scorecard, a rating for just how strong a dielectric superpower really is. All right, let's get the formal definition down, because this is very important for your exams. The dielectric constant, K, is defined as the factor by which the electric field is reduced inside a dielectric. And the formula is super simple. Just remember this. K equals E naught divided by E. That's it. Here, E naught is the original, strong field you started with, and E is the new, weaker field that's left inside the material. Since the field always gets weaker, E is always smaller than E naught. This means K will always be greater than 1 for any dielectric material. The only time K is exactly 1 is for a vacuum, because there's nothing in a vacuum to polarize.
Let's do a tiny example to make this rock solid, okay? Imagine we have an external field, E naught, of 100 volts per meter. Now we slide in a piece of dielectric material that has a K value of 2. So the question is, what is the new net field E inside this material? Well, we just rearrange our formula, right? E is simply E naught divided by K. So we just do 100 divided by 2, and we get 50 volts per meter. Simple as that. The material did exactly what its K value promised. It cut the field strength in half.
Okay, everyone, listen very, very carefully now. I'm telling you about a super common exam trap, a real silent killer that eats up marks. A lot of students get confused and think that a big K value means the material is a good conductor. This is 100% wrong. Please do not make this mistake. Remember the first thing we learned? Dielectrics are insulators. So what does a high K value actually mean? It means the material is an excellent dielectric. It is really, really good at polarizing and at weakening the electric field. So high K means a strong insulator, not a conductor. Got it? Don't fall for this trap.
All right, bachcho, we've covered a lot today, and you've all done a great job. So let's quickly summarize the main points, the key takeaways, and then we'll see where all this knowledge leads us next.
Okay, so for your notes and for your exams, these are the 5 golden points you must remember. Ready? Point number 1, dielectrics are electrical insulators. Full stop. Point 2, when you put them in an external electric field, their atoms polarize. They stretch. Point 3, this polarization creates an opposing internal field. Point 4, the result is that the net electric field inside the dielectric gets reduced. It becomes weaker. And finally, point 5, the dielectric constant, K, is the number that measures how much this reduction is. Boss, just remember these 5 points, and you are all set for this topic.
So you might be thinking, sir, this is all interesting, but why do we care? Why did we learn about materials that weaken electric fields? Well, the answer is huge. This ability to reduce the E field is the secret superpower that makes one of the most important components in all of electronics work, the capacitor. In our very next explainer, we will see exactly how putting these dielectric materials inside a capacitor allows them to store way, way more charge and energy. It's a fascinating and crucial application, so be sure to join me for that.